In this question, we have a look at an application of differentiation, which is an optimization problem. And it's recommended that you pause here and have a read of this question for yourself before we look at a strategy to go through and actually tackle this problem in the most appropriate way. Well, it's always wise to reread the question and ask yourself, what am I trying to do? An optimization question will rarely say this is a differentiation question or it involves calculus. You need to actually determine that by looking at what the question's asking. And what it wants to do is determine the dimensions that maximize the volume. So we're trying to achieve the maximum volume. Let's have a look at the question in a broken down form and see if we can actually analyze all the key bits of information. This is the time we need to be very patient and careful to take out all the bits of information that may assist us to solve this problem. So starting at the top, we can see that the shape is a cylindrical tank. That's obviously critical from the point of view of working out the volume formula. Now we've got some other information that's not tied in with volume, it's actually to do with surface area, but because it's numerical, factual information, it may assist us later on. So we can see that the top and base of the tank is made with material costing $100 per square metre. That's the surface area. And we can see the side of the tank is made from material costing $60 per square metre. At the moment that doesn't seem relevant to volume, but we'll note it because it may be assisting us later on. We're asked to determine the maximum volume, and we're asked to do that when the cylinder is constructed for a cost of $6,000. So that last bit of information is quite critical because it will tie in with the surface area information we had at the start of the question. So let's have a look at how we start this problem. The first thing we need to do, and we need to constantly remind ourselves of this when it's a word problem, is what is it we're trying to do? We're trying to maximize the volume. So what we need to do is address the volume formula first of all. Now being a cylinder, we know that the volume for a cylinder is equal to the area of the base multiplied by the height. Now in this case the area of the base is based on a circle, so it's pi r squared, and then we put down the h value. Now if we're going to apply differentiation techniques, we need to reduce this formula down to one variable, so it could be based on r or h. So what we need to do is look for other information that may help us. We know that we've got costs $100 per square metre and $60 per square metre, totaling $6,000. Now this information is tied in with the surface area. So we'll write the surface area formula down, and we know that because it's per square metre. Now the surface area of a cylinder is 2 pi r squared, and that's the area of two circles at the top and bottom of the cylinder, plus, now the outside part of the cylinder is basically a rectangle. We've got the height on one side of the rectangle, and the base is based on the circumference of the circle, so 2 pi r. So what we do is multiply those two together, like length times width for a rectangle. And that's our surface area formula. But what we want to do is incorporate the cost. We know that at the top and bottom it's $100 per square metre and $60 at the side. So it's 2 pi r squared multiplied by 100. In other words, every square metre is multiplied by 100 plus 2 pi r h multiplied by 60. And that's every square metre on the sides of the cylinder. So what we'll do is we'll simplify that, knowing the cost is $6,000 total. And we get 200 pi r squared plus 120 pi r h. What we need to do next is reconsider our volume formula, pi r squared h, and the cost equation, so we can reduce the volume formula to one variable. So what we'll do is we'll write down our volume formula again, which is pi r squared h. And what we want to do is replace one of these variables inside the equation, could be r or h, using the formula for costing. Now we'll notice there that we've got a h isolated there. There's only one term with a h. So what we might do is remove the values from the right hand side to substitute h back into the equation for volume. So first thing we'll do is remove the 200 pi r squared from the right hand side, move it to the left by subtraction, and that equals 120 pi RH. The next thing to do is bring the 120 pi r to the left hand side, and we can do that by division, isolating the h. So our h value becomes 6,000 minus 200 pi r squared, all divided by 120 pi r, and that now equals h. Now we can simplify the left hand side. We can do first of all the division of 10. That just involves cancelling the zeros on the top and bottom line of the fraction. We can also see with the values there that we can divide 12 by 2, and same with the top line. So it's a simple division to try and simplify that expression on the left. That means we get 300 minus 10 pi r squared divided by 6 pi r. And that still equals h, of course. Now we can see that you can do a further division. By dividing through by 2 again, we get 150 minus 5 pi r squared over 3 pi r. And that now involves h, which will allow us to substitute into the volume. So we'll write down here, because as our next step, we're going to use this h value to sub into the volume formula. So when we do that, we get volume is equal to pi r squared, and now we're going to multiply by this fraction, subbing it into the h. So it's 150 minus 5 pi r squared, all divided by 3 pi r. Now we can do a simplification. We've got pi r on the bottom line of this fraction, and we've also got pi r squared on the left. So we can divide 3 by a pi value, and we can also divide 3 by r, leaving 1 r on the left-hand side of the bracket. So when multiplying that out, we get 150 multiplied by r minus 5 pi r, in this case is cubed, r multiplied by r squared, all divided by 3. Now that we have the volume formula with one variable, our aim now is to use calculus to determine a maximum. So here's a visual representation of a possible maximum or a minimum. We can see the curve reaches an extreme value in both cases. In the first case, the gradient is 0 at that point, and likewise 0 at the minimum point. So in fact, I'll just indicate that with a 0. Now the gradient either side here is positive on the left-hand side, and then negative as we go across on the right-hand side. And likewise, when a minimum value occurs, the gradient is negative leading up to it, and then positive as we leave that stationary point. There are some possibilities that may be different to this. We may have a point of inflection, in which case a stationary point is neither a maximum or a minimum value. So let's have a look at how we do this with our equation. Often people have difficulty when a numerical denominator is involved. So what we'll do here is we'll just take that value of 3 at the front of our expression, and we'll make it 1/3. So 1/3 is the same as dividing by 3. So it's 1/3 of 150r minus 5 pi r cubed. All we've done at this stage is simplified our expression. Now let's differentiate it. And what happens is we get the 1/3 at the front, 150r becomes 150. The second term becomes 15, which is 3 multiplied by 5, pi r, and the power drops by 1 to become 2, or r squared. We can simplify that. So 1/3 of 150 becomes 50, and then we get 5 pi r squared, because 1/3 of 15 is 5. Now what we'll do is we'll let that derivative equal to 0 for the reasons we've shown in the curves above here in red. We want to determine if a maximum value occurs. So we place our derivative equal to 0 because that's going to determine a stationary point. When we do that, we'll solve it by taking the 5 pi r squared to the left-hand side, making it positive. Then we can divide both sides by 5 pi. And we can simplify that further by dividing by 5 to get 10 over pi. Now r is going to equal to the positive or negative values of the square root of that. Now when we're solving this, it's wise to consider all possible values. We know that the radius for a cylinder is going to be positive, in other words greater than 0. But what we should do when we're solving things like this is look at all the possible values and then isolate the solution at the end that's actually ties in with the problem, in this case a volume of a cylinder being a positive radius. The next step is to work out the derivative of the derivative, in other words a second derivative. Now the derivative of 50 is 0, it's just a constant. And the second part is going to be negative. Now 5 2's are 10, so negative 10 pi r. That's our second derivative, the derivative of the first derivative. And it's going to assist us to determine if our r value that we found is a maximum or minimum. Now r being positive, if we sub that into the second derivative, we know that negative 10 times a positive will be a negative value. In other words, the second derivative is negative. Now that's very helpful because we know now it's a maximum. And the reason why we know that is if we look back at our original graphs, we can see that the first graph, the gradient is decreasing. It's going positive, 0, and negative. So in the case of a maximum, our derivative is going down. It's decreasing towards a negative, and that means the second derivative, which is the derivative of the first one, will be negative. It's showing the change in the first derivative. And in the case of a minimum value, the gradient's going from a negative to 0 to positive. The derivative in the case of a minimum is increasing. So the second derivative will be positive. It's showing the change in the first derivative. So a negative second derivative tells us we're going to have a maximum value. Let's have a look at our solution now. Now we know the radius is going to be positive, and we can substitute the square root of 10 over pi into our calculator. We get a result of approximately 1.78 meters to 2 decimal places. Now we can determine the h value using the exact value for r, and that's the equation that we had earlier, which we substituted into our volume formula, which was 150 minus 5 pi r squared all over 3 pi r. Now substituting the exact value of r into our equation, we get approximately 5.95 meters to 2 decimal places. Now we've got the h and the r value, and in the original question all we're asked to do is find the dimensions. But what we'll do in this question, we'll go a step further and we'll find the volume of our cylinder to determine the maximum volume. Keep in mind a question may ask you for the dimensions or the actual maximum or minimum, or sometimes it might ask you for both. So we know the volume formula for a cylinder is V equals pi r squared multiplied by h. And we can substitute both the radius and the height into this formula, and the result we get is 59.47 meters cubed, again to 2 decimal places using the exact values. Now the original question was asking for just the dimensions, so we'll summarize this by answering the question in words, because the original question did ask us in words for the dimension. So the dimensions to give a maximum value are radius approximately 1.78 meters and a height of approximately 5.95 meters.